was really what happens if you drive this with a current source instead of a voltage source. And how did you go about doing that? Yeah, so the easiest thing is, this combination of Vs and Rs can be thought of as a current source in parallel with Rs. So you do that, and then it was driven by an ideal current source, so you send Rs to infinity. Okay. So you had V naught by Vs equals some transfer function, okay, and Vs is nothing but, if I transform it into a current source, it will be Is times Rs, okay. So V naught by Is will be Rs times H of S, but then I want to drive it with an ideal current source, so that means that I have to take the limit of Rs going to infinity, okay. So that's all that's there to it. What do you get for the poles and zeros? So one of the poles will be at S equal to 0, because in the circuit you see that the current source is driving a capacitor, right? So at DC this is an open circuit. So at the input of across the current source you get infinite voltage, okay. As the frequencies increase, these currents will go through this current will go through the capacitors, and you get smaller and smaller voltages, okay. So the poles will remain more or less the same as before. One of the poles will be at 0. Where is the other pole? Where is the second pole of the transfer function? Where was it before when we drove it with the voltage source? Huh? 1 by? No. Was that where it was? Yeah. So here it is. It's approximately Gm by Cl, right? If Cc is large, or it is some fraction of Gm, the second expression here, divided by Cl. So that's what it's going to be even with the current source. Okay. So if you drive it with a better and better current source, it becomes more or less an ideal, it becomes an ideal integrator. So let's say you plot the magnitude of V out by Is, and let's imagine that there is some Rs, okay, that Rs is not infinite. And then there is a 0 also. The magnitude will do this, okay. So this is P1, P2 and Z1. So what happens if Rs increases? Huh? What happens if Rs increases? It becomes 40 dB. Huh? Yeah, okay, so how will this plot change? It will become, this is minus 20 dB. So it does this. Huh? Why does it do this? Does it do this, or does P2 also shift? P2 and Z1? Huh? P2 will not shift. Okay, and what about the 0? Now, is this what happens? What do you think will happen? What happens to the DC gain? V out by Is as Rs increases. Huh? So it will not shift like this, it will do this, right? the same line will keep getting extended as you keep on increasing RS. And in the limit of RS being infinity, it becomes an ideal integrator. Okay. So if you drive it with another current source which is ideal, you get an ideal integrator. And that again we'll see is one of the types of op amps we'll use in feedback systems. Because I mean this Bode plot does look like something that we would want to use in feedback systems, right? It has a nice 20 dB per decade slope all the way from very low frequencies to a point after which it crosses. I mean here I shouldn't say unity because unity, I mean this is a dimension quantity and the unity of this doesn't make any sense. I mean, it doesn't have any significance, okay? But it does have a 20 dB per decade slope for a large range of frequencies. So it's a very simple transformation of the other case. The only thing I wanted you to get was that the pole will go to the origin if you drive it with an ideal current source, okay? Any questions on this or the second problem that we discussed? Okay, so second meaning I mean the input impedance of the source follower. So that turns out to have a negative real part. So you can use that to make an oscillator or using either an inductor and a capacitor or using a crystal. Okay. Are you familiar with this circuit? This is a crystal. So this is a crystal oscillator. Have you guys seen this? So the basis of this circuit is exactly the same as what I discussed earlier. If I just write the signal picture, okay, this point is grounded, right? Basically it is shorted to this. And this offers a negative resistance. Now this is a transconductor. It doesn't have to be a single transistor. It can be multiple transistors. Okay. Now normally in the analysis we thought of this as ground, but let me remove this and put the ground here. Okay. Actually there are capacitors here also in the oscillator circuit. As because this offers a negative real part, I can connect a crystal here. Again, I remind you that this doesn't have the biasing arrangement that is shown. Once you put the biasing arrangement, it will become complete. So if you put the crystal here, it becomes a crystal oscillator. If I rearrange this, redraw this circuit, what do I get? This is the ground. The source is grounded. Okay. There is a capacitance from the gate to ground and also this is the drain. So there is a capacitance from the drain to ground, and the crystal is between the gate and drain. Okay. Now, as I said, this really has to be some transconductance, not necessarily a single transistor. Now you can use an inverter as a transconductance if it is biased properly. Okay. In fact, this also has something to bias the inverter correctly. So I can have a PMOS also in parallel with the NMOS structure. So the transconductance is realized using the inverter, which is biased around its high slope region, and you have a capacitor on either side, and you have a crystal. It's exactly the same circuit as this, but with the ground shifted. So we analyze the circuit with the drain being grounded, whereas here we think of the source being grounded. Okay. So it's a very common crystal oscillator that you see, especially in digital circuits. You have this crystal oscillator to generate the clock. So that's the usefulness of the negative resistance, but when you are trying to make an amplifier, it's a problem. So we also found out how to compensate that problem, because we could split the impedance into a parallel combination of a capacitor and another branch which has a negative capacitance and a negative resistance. So if we put the same series combination of the same capacitance and resistance but positive ones, we'll cancel it off and we'll be left with only the input capacitance of the circuit. Okay, that will stabilize the amplifier. So if you look at old high-speed amplifier circuits, lots of them are like this. Okay, because it was quite common to use bipolar emitter followers. In fact, many of them to get very strong buffering. When you have that driving a heavy capacitive load, you will get a very high probability of instability. To get rid of that, you connect a series RC at the gate. Okay. Any questions on this? So the next problem was again using some control source. As I mentioned earlier, all of this are relevant to some circuit that we'll come across later. Okay. And here you have Vx and you have Gm times Vx. And the question is, what impedance do you see looking up? Okay. What is the impedance you see? What is the impedance you see with Rs being 0? If Rs is 0, what's the impedance you see? Minus 1 by Gm. So the controlling voltages in this sense. So if you put Rs equal to 0, you get this. Again, Vx is this way, right? So if I apply some V test, a current of G times V test will flow here. Current of SC times V test will flow here. So the impedance is 1 over SC plus Gm. Okay. So here whatever you get, if Rs goes to 0, you have to get this one, right? So what impedance do you get with Rs not being 0? What kind of impedance would you get? Like a high pass type of impedance, low pass type of impedance? What is the? How would you make a judgment? If I plot the impedance versus frequency, will it increase with frequency, reduce with frequency? Huh? It reduces with frequency. Why? Yeah, that is okay. So one part of the impedance is simply the passive components that we have, right? So whatever components are here will appear in the impedance. I mean, the impedance of this branch will appear. But the more interesting part is we have a control source. So we can think of it as an admittance contributed by this branch and another by the control source. And the two will appear in parallel, right, in the final picture. There will be some current flowing into this and some flowing into this, and the two will appear in parallel. And this, of course, will be simply series RC combination. But the more interesting part is through Gm. What will that look like? Will that impedance increase with frequency, reduce with frequency, stay constant with frequency? Okay. Okay.
Which means that impedance will actually increase.
The impedance will increase or decrease? Decrease. How many say decreases? How many say increases? I mean, it has to be one of the two, right? How many say constant? How come? I mean, the sum of the three should be everybody in the class. Huh? Okay, let's take a vote again. How many say increases? Impedance increases. Okay, there is no abstaining this vote. Okay. How many say it stays constant? How many say it decreases? How many have no opinion of the impedance? Huh? So this is not a political issue, right? You can voice your opinions very easily. So what's the verdict? Huh? Decreases. Okay, let's see. Why do you say it decreases?
Because at s equal to 0, the capacitance is open. So
Okay.
it's 1 by GM. And at s equal to infinity, you have something like that.
Okay. Okay, let's see what happens.
S equal to infinity, we have the capacitance
Yeah.
GM into Vx is
Yeah. So what happens? It decreases. No, I mean you gave the right reason but the opposite conclusion, right? There are a couple of ways to think about this. First of all, what is Vx as a function of, if I have Vtest here, Vx by Vtest, what happens to this quantity as a function of frequency? Huh? It reduces. It's a low pass filter, right? So what happens to the current as a function of frequency? It reduces. And the voltage is fixed. So voltage divided by current increases, right? So, no, what you said was, yeah, at s equal to 0, this is an open. So you have all of Vtest coming across Vx. Okay? So you get 1 over Gm. At s equal to infinity, this is a short. So this actually opens out. Okay? So the impedance actually increases, right? So the analysis is pretty simple. So essentially, the current here, this current is Gm times, what is Vx by Vtest? It's a low pass filter, it's just drawn differently, that's all. It's the voltage across the capacitor that we're interested in. Okay? Gm times 1 by 1 plus SC Rs. This is the admittance contributed by this current. Okay? Plus whatever we have here appears in parallel. What is the admittance of this branch? So series combination of Rs and SC. Okay? Now this itself can be rewritten as 1 over 1 over Gm plus SC Rs by Gm and this. So it's a parallel combination of two branches, each of which is a series combination of two elements. Okay? What is this branch? This is what we know already. It is Rs and C. And what is this branch? It's a resistance of 1 over Gm in series with the impedance is proportional to S. Okay? And what's the value of the inductance? CRS by Gm. So as you can see at DC the inductance is a short, so you get 1 over Gm. Okay? At very high frequencies this branch is an open, this C is a short, so you get 1 over, you get RS as the impedance. So if you do plot the Bode plot, it will start from 1 over Gm and it will go to RS. Okay? This is what it will look like. So in this region where the impedance is increasing, it shows an inductive behavior, and that's the interesting part of it. We don't have an actual inductor, but we do get inductive impedance. This again is familiar to you using gyrators and other concepts that you have learnt in other courses. You can get inductive behavior by using only capacitors and control sources. The idea is that an inductor integrates the voltage to give you a current, whereas a capacitor integrates the current to give you a voltage. By using control sources, you can swap the current and voltage. So instead of getting an integral of the current, you can get an integral of the voltage by using appropriate control sources. That's what a gyrator is, right? So this is some very simple realization, a single transistor realization. Again, this is the equivalent, the small signal equivalent of a transistor, and it will have its own CGS, and you can add some capacitance if you wish. And if you put a resistance in series with the gate, it will look like an inductor looking from the source. Okay. So this is again some circuit technique that is used sometimes. You use inductances to extend the bandwidth. That is, sometimes because of capacitances you get limited bandwidth. Now you have an inductance, you get a slightly enhanced bandwidth. So you can use this. Okay. You can use this active technique. This is an active inductor. I mean, one realization of an active inductor. There are many of them. Any questions? All of you realize that it's an inductor? What was the passive equivalent that you derived? Or did you derive something different from this? Everyone got this? What is the order of the system? I mean, this circuit, we have 2 R's and C and an L. What is the order of the system? First order. Why? No, I don't know. But looking at the circuit, why do you say it's first order? I have a capacitance and an inductance. And there's no trivial case, right? First of all, I have two different kinds of things. And it's not like the inductance is across a current source or something like that.
You take C as the voltage across C as state variable.
Yeah.
Then you can express the current to the inductor because it's.
So, I mean, in this case, of course, there is only one capacitor. So, looking at this circuit, it's very clear, right? Looking at this circuit, what about looking at this? Why does it turn out to be a first order system? I mean, we know it is first order, right? First of all, if you look here, it has only one capacitor, so it can't be more than first order. And we evaluate the impedance, it also looks like a first order thing. But if I look at this circuit, if I didn't know anything about it, I would probably say second order.
The current to the inductor can be expressed as the voltage of the capacitor because it's in series. I mean, like the current to the capacitor is same as the current to the inductor.
No, that doesn't matter, right? I mean, why? The voltage across the capacitor, the state variables are voltage across the capacitor and current through the inductor. I can do that here also, like what order is this? What's the order of this system? Second order. So why is this first order? I mean, in fact, huh? We have only one loop? Okay, what about the order of this system? Huh? Second order. So what about
if you write CdV by dt,
yeah.
not the current to the inductor, but in the previous case it is written.
No, I mean, that is because I have not connected the source, right? I can do this also. No, that is not the reason. Why is it? Let me ask you something else. I have. Exactly. That's the reason that I was in fact going to ask what happens in the general case when you have this. It is a second order system, but there are two time constants associated with this. Okay. Sorry. CR1 is one of them and L by R2 is the other one, and they are the same in this circuit. So you have a sort of pole zero cancellation. Okay. So if you write it in terms of general values, you do get it to be a second order system. But in this case, I mean, it's effectively restating that the inductance is generated by some control source. So the time constant of the current here through the control source is exactly the same as the time constant of this branch. So the time constant of the two branches are the same. So you get it to be a first order system. Okay. So if the time constants were different, you do get a second order system. But in this case, by design, the time constants are the same. So you can try it out. You can, instead of 1 over Gm, you put some other resistance and you do get a second order impedance. Okay. In fact, the trivial cases, I make these two resistances 0, right? So then I do get a resonant circuit. Any other question? What is the next problem? The bipolar. Yeah. So the next question was again, this is sort of nonlinear circuit analysis, but it's a rather trivial circuit anyhow. Huh? PNP, okay. This is like this. Okay. So what is V1? And if the area of this is, let's say, A0, what is V1? So the saturation current density is given as Js. So saturation current is A0 times Js. So V1 is Vt ln I0 by A0 Js. Okay. So next, the other branch was and this is some n times A0. It has a larger area. What is V3? N times A0 Js. Basically, it's the same voltage as before minus Vt ln n. Okay, it's some fixed offset from the whatever the value of I0. As long as same I0 is flowing through the two branches, the V3 here is a shifted version of V2. Okay, the shift is fixed for all values of I0. What is V2? V3 plus I0 R. So it has some values, and that by itself is probably not too interesting. Now the question was, what is the value of the current when V2 happens to be equal to V1, right? If you want to make V2 equal to V1, what must be I0? So that's all. Like here I have V2 is V3 plus I0 R, and I want to make that equal to V1 minus Vt ln n. Okay, and I want to make that equal to V1, and V3 is V1 minus It ln n. So I0 is Vt ln n by R. So what is interesting about this? So it is proportional to absolute temperature. It actually doesn't depend on A0. It doesn't. It depends only on R and Vt. Okay. So that is actually a very interesting property of this circuit. Now, what will be the GM of this transistor? Let's say we do choose this particular value of I0 to bias the transistors. What will be the transconductance? Yeah. Of which one? This one or this one? Both. So the transconductance of a bipolar transistor depends only on the current flowing through it. Okay. So the transconductance of each of them is it's I naught by Vt, so it is ln n by R. So this again is very interesting because you can set the small signal transconductance of some nonlinear component to be exactly equal to the conductance of some passive component. Okay, that is why this circuit is interesting. Again, this circuit is very often used to, let's say, maintain the transconductance constant. Okay. So I will plot V1 and V2 with respect to I naught. What was V1? V1 was some Vt ln I naught. I mean, it is increasing, of course, but I naught by A naught Js, and V3 was some fixed shifted version of this. Okay. What will V2 look like? What is again shifted? If I want to plot V2, what does it look like? Will it shift up or down? Shift up by Vt ln n. So it will become equal to V1. So actually the amount of shift depends on the current. Okay. So if I plot I naught R, it will be, let me draw something like this. Okay. So the shift will be very little here, but then the shift will go on increasing, and at some point it will cross this. Okay. So that was the point at which the transconductance was equal to 1 over R. So this is V2. Okay. So if I plot V1 minus V2, what does it look like? Or maybe V2 minus V1 is easier, but it will, V2 minus V1 will be 0, and then it will have, sorry, what happens at very small values of I naught? It will become equal to Vt ln n, right? It will do this. Okay. So V2 minus V1 will cross 0 at the desired value of I naught. In fact, that was the definition of our I naught. I mean, the desired value of I naught. Okay. So this is desired from the point of view of getting a transconductance proportional to the conductance of the resistor. Okay. So can you propose a circuit that will bias the circuit at this point? So now I said, I mathematically calculated, I said, if I'll find V1, V2, and then if I somehow make them equal, the transconductance equals 1 over R. But, I mean, I can't sit and tweak that, right? So how will I do this? I want to somehow automatically adjust I naught so that this V1 minus V2 is 0. So what's the general idea? We'll have to use feedback. Okay. What do you sense? You sense V2 minus V1, and then what do you do? So if V2 minus V1 is positive, you increase the current, you decrease the current, and if V2 minus V1 is negative, you increase the current. Okay. So this again, it's sort of jumping ahead of the plot a little, but if you keep this in mind later, we can go through some of the other circuits more easily. We need a controlled current source. So I think you already know that we can use a transistor to do that. It has to be in the right region and all that, but we can use this. And to increase this current, what do I need to do to this voltage? So this is V1, this is V2. I have to reduce this voltage. Okay. So what is the sense of the feedback? So I wanted if this is the plot, this is what I want, right? So how do I assign the signs? Huh? Which is the left one? I mean, if you say plus minus, I don't know where to put it. Left is plus, and this is minus. Huh? Is this correct? No. It is correct. So let's see what happens if V2 minus V1 is positive. It will reduce this voltage. Okay. Somehow something is wrong here. Yeah. No, why? What happens if PMOS is used? No, when should you increase the current? Yeah. So it's not really the PMOS thing. We already said that we have to reduce this voltage to increase the current. Right? We have to increase the current when V2 minus V1 is negative. Okay. So when V2 minus V1 is negative, this tends to move down. Right? So this circuit will bias itself at what current? So when the bias is stabilized, it can be VT ln N by R. Are there other possible bias points for this circuit? Zero. I mean, you can have all zero currents and nothing will happen. So we'll see how to get out of those situations later when we come to circuit design. Okay. So this is very useful because it generates a current that is proportional to absolute temperature, and it's known as a p-type circuit. So the next problem is very similar to this. In fact, if you somehow replicate this with MOS, although they are very different non-linearities, it turns out to have a very similar effect. Okay, it's not proportional to absolute temperature, but what did you get to be the transconductance of the MOS transistor? I mean, how was it related to R or was it related to many other things? It is inversely proportional to R. That's what you should have got. Let's quickly go through the analysis. What is V1? Okay. This is V1. I think the resistance was in the emitter, right? Source. Doesn't matter. It's the same thing. And what is V2? It's I naught R plus the VGS of this transistor. Okay. So when is V1 equal to V2? When this equals I naught R. Okay. So it looks like some complicated dependence, yeah, and the expression is complicated. But again, the interesting question is what happens to the GM of the transistor. Okay. So what is the GM of the transistor in terms of current in saturation region? Mu Cox W by L. Okay. And what is I'll cancel this off. I get square root I naught here. So I substitute square root I naught in this. I get it's this times square root of I naught, which is times 2 by mu Cox W by L times something, this quantity in parenthesis, times 1 by R. Okay. So this goes away. So it is some fixed quantity. I mean, this quantity is not related to any of the physical parameters of the transistors. It's only related to the geometry, right? So it is inversely proportional to R times some scaling factor that you know, because you can, that is one thing that you can adjust in an IC, that is the ratio of geometries. In fact, it's not the geometry itself, but it's the ratio of the geometry of two transistors. Okay, N can be accurately adjusted, as we'll see soon. So here also it so happens that the transconductance of the transistor is inversely proportional to the conductance of some passive component. Okay, this is again a useful circuit. Like one reason, just to give you an idea of why it is useful, let's say you make an amplifier. What's the gain of this amplifier? Minus GMR. Okay. So if GM happen to be inversely proportional to this R or some similar type of R, then the gain will be some fixed quantity, right? If GM is some A by R times R, now GM will have temperature dependence, R will have temperature dependence and process variations, but you can keep the product of the two constant. That's the motivation for using some circuit like this. Okay. So it does turn out to be a useful circuit. So you can in fact try and get an accurate gain without using feedback. That's the key here, right? There is no feedback in this circuit. It's still GMR, but somehow you have adjusted the GM to vary inversely proportionally to R. Okay. So similar thing for the bipolar also there, except one more. It's also a little more useful because you know the exact temperature dependence. Okay. So you can use it as a thermometer, for instance. You get that. You somehow use that circuit and then you get the current or some voltage out and you get something proportional to the absolute temperature. So that's a thermometer. You can monitor the temperature on chip. So if you look at a computer, you have temperature sensors, right? So you can have something reporting the temperature inside the chip if you have the right kind of circuit. Okay. So that's also where it's useful. You can have on chip temperature sensing. That's not the only way to do it. There are some disadvantages to it, but that's one way to do it. Any questions on those two circuits where we got GM to be proportional to 1 over R? We'll come back to these circuits towards the end of the course and we'll complete it, because now we are saying you put feedback here and so on, but we'll complete the details of those at the transistor level by the end of this course. Okay. So if there are no more questions, we can go to this. So F is some nonlinearity, beta is the feedback fraction, so you get V naught times beta here. Was everyone able to solve this problem? Huh? What did you get to be the answer? What's the idea? What's that? So F is some nonlinearity, but what's the bottom line? What do you get out of the circuit? G is similar to F. Okay, that's not very interesting, right? The nonlinearity reduces drastically. That's what you should have inferred, but let's analyze it and see. So this is V naught is F of whatever voltage is here. Okay. So if this is some, this is the error voltage VE, it's F of VE. So V naught is F of VA minus V naught beta. Okay. What is the operating point of the circuit? I had given that F of 0 equal to 0. So you can by inspection see that if VI equal to 0, V naught equal to 0, everything is satisfied. Okay. So the operating point of the circuit is okay. So because when you expand a nonlinearity in Taylor series, you have to choose some point about which to expand the function. And in this case, we will choose 0 because that's the operating point of the circuit. Okay. So how do we go about solving this? What I had asked for was V naught will be, this is some implicit equation, G of Vi. Now, you can't explicitly solve it without knowing F, and in some cases, even if you know F, you can't solve it. So, what I want is G as a Taylor series. Okay. What is the first coefficient? 0. What is the second coefficient? How do we solve that? So, the first coefficient is basically related to the first derivative of V naught, right? I want dV naught by dVi. That's what I want to calculate. It's actually quite a simple calculation, but sorry. Okay. So, and at the operating point, this whole thing is 0. So, you get dV naught by dVi to be is okay. What is this quantity? Huh? It's a gain of a closed loop system. If f was linear, this would be exactly, I mean, it could be a linear transfer function with this gain, right? So, f prime is nothing but the slope of the curve. That's what we think of as a gain of an amplifier. Okay. If f is an amplifier, f prime is the gain of the amplifier. Okay. So, and if f happened to be a straight line, then this is simply the gain of the forward path divided by 1 plus the loop gain. Okay. And if f prime is very large, it will be 1 over beta, as you expect. This is okay? Everyone was able to recognize this? Fine. What do you get the next term to be? I'm not sure we'll have enough time to solve the whole thing. So, you successively keep on differentiating this and you get this. Okay. So, you will get something divided by 1 plus cube. Now, this is the coefficient that you get here will be related to the second derivative of f. Okay. Now, if the loop gain is large, this will become very small. That's the general idea. Okay. So, this is how you can use feedback to linearize the system. So, I won't solve it. I think it's a lot of algebraic manipulation. Probably a lot of you have got it. If you haven't, let me know. I'll solve it explicitly. But you should get this, and then for the, what do you get for the third term, cubic term? For 5 or 4? 5. Yeah. So, fine. That is there. So, you get something, let's just stick to the first two terms. Here we get to the power of 1/3. Okay. So, I'll sort of pose a puzzle and then we can stop the discussion of the assignment. This is f. This is beta, Vi, V naught. Okay. Now, let's say f is sort of mildly nonlinear. Okay. And we also said that V naught is 0 plus so that's how it goes, right? Now, let's say that overall, I mean, f itself is mildly nonlinear, and let's say you have a large loop gain. So perhaps we can neglect all of this. Okay, at least those terms are small, very small enough to be neglected. What will be this voltage? V. Assuming that we can neglect the higher order terms, I mean, or at least it's a mild nonlinearity, it's a reasonable thing to do. We keep doing this all the time, right? So, is Vi by? So, this is what we get. Okay? And if the loop gain is large, this is a very small quantity. That's the idea. So, is it clear how the nonlinearity is reduced? If f is like this, let's say, this is f versus VE, f of VE versus VE. And if you applied the input directly without feedback, let's say the input would be swinging over the nonlinear part of this. Now, when you have feedback, the amplitude of the input to the nonlinearity is drastically reduced. So, it swings only over a very small part. Okay. So, you can think of that as how the nonlinearity is reduced, right? Is this part clear? I am saying with feedback, you are reducing some part of the input. Basically, you are subtracting something from the input. So, the amplitude to the input of the nonlinear block is smaller. So, effectively, the nonlinearity, you can expect it to be smaller. Is that a reasonable argument? Okay or no? Okay. So, now let's go to the next part, which is more interesting. Now, what is the output? It is, the first term we said was 0. Okay. That's what we have, right? Is this correct or no? So, this is, I mean, this is in terms of the input to itself, the nonlinear, V is the input to the nonlinear block. This has to be right. Is this okay? Now, what did we say VE was? The input divided by 1 plus f prime of 0 beta. Okay. So, let me substitute it here. That is the first term. And here what do I get? F double prime of 0 by 2. Okay, let me put this 2 here. 1 plus f prime of 0 beta square. Okay. This is basically, I am taking VE square, right, times VI square and so on. So, just by inspection you can see that the next one will be 1, I mean, to the power of 3, 4 and so on. What is the problem? No, operating point is 0. Yeah. Okay. So, I mean, let's say it is very small. No. This is a functional dependence, right? There also you get f double dash of 0, isn't it? When you do the exact analysis, you also get f double dash of 0 in the numerator. But you get 1 plus f prime in the denominator. No, it is true. I mean, something has been neglected here, so that's why you get the wrong answer. But think about exactly what it is that gives you something like that. Yeah, which is VE, right?
Yeah, so there will be some other terms also which has to act.
Which one?
You are doing a transformation from.
No. I mean, I have VE as the input to the nonlinearity. The only thing I did was to approximate the value of VE, right? That's all. Isn't it?
You are going from E naught equal to G of VI to another variable. So there will be
No. Why? That is VE, right? I mean, it's just a notation. VI minus V naught times beta is VE. That's all. No, it is true that it is because of neglecting terms I will get this, because the one is exact analysis, the other one is looked like it was going intuitively in the right direction, but then it didn't go all the way or something happened. So, you figure out what that is, okay? In fact, you can simulate it and see exactly. You can put a sine wave, you assume some f, it doesn't matter. In fact, you can assume f so that all these other extra terms are in fact small, okay? But then you look at the waveforms here and there and then see what happens. Okay. So it is true. It is because of neglecting other nonlinear terms. There is no question. But you look at the distortion components and see why it behaves like that. Huh? No, the only thing is here I got, here it is cube, which is I think what you would have got. Can you see this? Yeah. This, I think you can't see this. Should probably move the screen. So here I have cube, but then I made some approximations to compute the value of VE, and then I expanded the whole thing in Taylor series, and here I have got square. Okay. So which implies that the reduction in nonlinearity is not as much. The intuitive reasoning where we said VE is this and neglected all higher order terms does predict a reduction in nonlinearity, but not as much as reality. Why is that?